Hi and welcome back to Gaffy's Grinds. This is video 3 in our series on radioactivity for Leaving Cert Chemistry. If you haven't already watched videos 1 and 2, you should check them out first. Otherwise, this video is going to be a little bit more complicated for you guys to understand because some of the ideas from there lead into this. The usual reminders, do eliminate any distractions by closing any social media tabs and any other unnecessary tabs you have open, and try and stick your phone on do not disturb mode. Just eliminates distractions. And the most important thing is I'm going to give you things to do while we watch the video. I'm going to ask you to write things down. I'm going to ask you to do some questions, and you should do those. If you don't, you're not going to learn very much by watching the video, pretty much wasting your time. So we're going to start by answering a few questions to make sure that we do know the stuff from the previous videos, because it leads into today's video. So I've got set here questions for you. So from memory now, without looking back at your notes or anything from the previous topic, I want you to try and answer these questions for me. Pause the video and then play for the answers. Okay, so you should only hear my voice if you have paused and you've tried the questions. Here are the answers. They're pretty straightforward, I think. Nothing in there that's really going to catch you out. So I'm just going to show you the answers, and you can pause to make corrections. All right, with that in mind, those answers are important. Keep them in mind going into today's video. They're absolutely important things that you need to know in order to answer or to understand today's video better. Okay, so today we're going to be looking at what we call the properties of alpha, beta, and gamma radiation. So these are our 3 types of radiation, and they basically get emitted from unstable atoms. So say we have a rock or a metal, a piece of rock or a piece of metal, and it is a sample that contains a lot of unstable nuclei. We've got this little square here. Let this represent a rock or metal sample, and it's got a lot or significant number of unstable nuclei. We call this a radioactive source. So a radioactive source is a lump of material, be it metal, rock, some kind of a material that's got a lot of unstable nuclei. Now, generally, if scientists want to study the radioactivity, what they'll do is they'll put a case of lead around it. Now, we'll talk about why lead later on, but just know they use the material lead. Now, the reason why they do this is because this substance, this piece of material, is constantly emitting radiation, and it emits it in all directions. Now, because it's emitting it in all directions, it's difficult to study. So what this does is it creates a little slot so that the radiation can be directed to where the scientist wants it to go. So we use a radioactive source, which is just a piece of material which has a lot of unstable nuclei, and it will be firing out radiation. And then they use a case around it to block the radiation from going in all directions and just study the radiation as it comes in one direction. Now, the first property we're going to talk about is how are the different types of radiation affected by an electric field. Scientists will apply an electric field by taking an anode and a cathode, which are positively and negatively charged plates. So, anode, cathode can be seen here as positively and negatively charged plates. So this is the anode, and this is the cathode. Together, they create what we call an electric field. The electric field is in here. It's this area in here where the charges are going to have their effect. So that's what we call an electric field. Now, let's look at what happens to each type of radiation as it would travel through an electric field. So I'm going to use an orange line to show what would happen to beta particles. So imagine this radioactive source is a source of beta particles. So as the beta particles would travel out of the case, what would happen to them? Beta particles. Well, in our questions, we reviewed that beta particles have a negative charge. So because of that, we know the rule is that opposites attract. Should know that from our bonding. And beta particles will end up being deflected up here. Beta particles. So the angle would actually be changed. Beta particles. Why? Well, they are negative. Beta particles are negatively charged. So beta particles negatively charged. Now I'm actually just going to move that up a little bit. Now, guys, you shouldn't be writing frantically trying to copy everything down. Do please listen to me. It's much more important than trying to copy. Okay. Now, what would happen if instead this radioactive source was a source of alpha particles? We know that alpha particles have a positive charge. So as they travel through the electric field, they would begin to be attracted towards the negative plate because they are attracted to the oppositely charged plate, and they would end up being deflected in this direction. Is what we call an alpha particle. Is down here. Alpha particles are attracted to the negative plate because they are positively charged. So alpha particles are positively charged. So they are attracted to the negative terminal or the negative plate of the electric field. The last type of radiation, let's imagine we're talking about gamma radiation. And gamma radiation is always emitted when one of these particles is emitted. Well, what's going to happen here? Well, gamma radiation is shown by the red line here. Gamma radiation has no charge. It's neutrally charged. So it is completely unaffected by the electric field. So gamma radiation goes in a straight line. Nothing happens to it. It is undeflected or it is unaffected. Gamma radiation. And gamma radiation is what we call neutrally charged. Neutral, no charge. All right, so we're ready to answer some questions now. Don't worry about taking that down because you're going to have to do it in the questions, okay? So here we go. Question 1. What is radioisotope? So you should remember that from the previous video. Question 2. What is a radioactive source? So I'll just explain what a radioactive source is for you. This should be number 3. Sorry, I'm just going to fix that. And this is number 4. State one difference between gamma radiation and the other types of radiation. And then number 4, alpha, beta, and gamma radiation are fired through an electric field. Explain what will happen. Use a diagram to help. So again, without looking back now from memory, try and draw out a diagram to explain what will happen. Okay, so pause the video and do that now, please. Okay, so what is a radioisotope? A radioisotope is an isotope with an unstable nucleus. Okay, so you should have mentioned unstable nucleus. You should definitely have this phrase in your answer. Unstable nucleus. So an isotope with an unstable nucleus. Now you should have a full sentence. I am just telling you the key bit you need to have in there. What is a radioactive source? Well, it's a material, and it has a lot of unstable nuclei. Okay, state one difference between gamma radiation and other types of radiation. Well, you could have said it has no charge. That would be one difference. I suppose the main difference is it's not a particle. It's energy. It's energy. It's not a particle. So alpha and beta radiation are particles. Gamma radiation is just a wave transferring energy. So it's just energy. Alpha, beta, and gamma radiation are fired through an electric field. Explain what will happen. Use a diagram to help explain. Okay, so this is the diagram, the one we drew over here. So you should have a radioactive source, an anode and a cathode, creating an electric field. And you should show that beta particles are attracted towards the anode. So you should mention that in writing. So as well as drawing, you should say beta particles attracted or deflected, attracted to the anode or the positively charged plate. Gamma radiation, we say, is unaffected, no no change, nothing happens to it, goes in a straight line. And alpha particles is attracted to the cathode. To the cathode. Okay, so alpha particles get attracted to the cathode. So you have your diagram and you have your sentences explaining what's happening. All right, good. That's the first property, is what happens to them in an electric field, alpha, beta, and gamma radiation. Let's look at another property now. All right, so say here, I am drawing a nucleus of an unstable nucleus, okay? I'm drawing an unstable nucleus. So here I am drawing some protons. I'll change the color to purple, and here I'm drawing some neutrons. I've got my protons and neutrons. This is a nucleus, and this nucleus is unstable. Okay, so this is an unstable nucleus. What can happen is that we can have three types of radiation. Let's take a look at, for example, gamma radiation. This is gamma radiation. When gamma radiation leaves the unstable nucleus, what's going to happen is it's going to eventually encounter another atom. Now, this is a second atom. This is an atom. I'm drawing the protons. I'm drawing the neutrons in the nucleus. But we also have electrons on this atom. Electrons. Oops, sorry. Let's get back to the shell. Thank you. Electrons. Here are my electrons. Now, if radiation crashes into another atom and knocks an electron out of the atom, then that has basically turned this atom into an ion. So where we have radiation, it can knock electrons out of atoms, turn them into form ions. Can you think back to our previous topic where we studied trends in the periodic table? What is a word for that? How would we describe this radiation? What type of radiation would it be? A word for what it does. Okay, so on 3, speak your answer to the screen. 1, 2, 3. Okay, I'm hoping that you said we call this ionization. Ionization means to create ions by removing electrons. So this radiation is capable of knocking electrons out of other atoms. Now, all of these nuclear radiations, all of these radioactive emissions are capable of knocking electrons out of atoms. Now, if we take the second type of radiation, we look at beta particles. Beta particles. Remember, a beta particle is essentially just an electron. Now, when we take a beta particle and it crashes into another atom, here is another atom, here is the nucleus, and here are some electrons. Okay, now the beta particle is bigger than the gamma radiation. So if you remember, this was gamma, and this here, the second one, this is beta particle, different types of radiation. The beta particle is bigger than gamma. Gamma is just a wave. Beta particle is actually a particle. When it knocks into the electron, it has a better chance of knocking that electron out of the atom. So we say it has a higher ionizing power, high ionizing power. Beta particles have a high ionizing power. Gamma particles have a lower ionizing power. Just actually going to move this, sorry. Kind of in the way. Low ionizing power. So gamma rays have the low ionizing power. Beta particles have a higher ionizing power. The biggest type of radiation is the alpha particle. It's made of 4 particles, 2 protons and 2 neutrons. Bigger than a beta particle. The biggest type, much bigger than an electron. When it encounters an atom, it crashes into an atom. Here is this atom. So we've got electrons in this atom again. The nucleus. When the alpha particle crashes into the atom, it actually has a higher chance, because it's the biggest particle, biggest, heaviest particle, it has the highest chance of these 3 types of radiation of knocking electrons out of that atom. So the alpha particle has the highest ionizing power because its mass is bigger, which means it's going to hit it harder and knock electrons out. Okay, so that is our ionization, is where radiation can knock electrons out of atoms to form ions. Gamma radiation has the lowest ionizing power. Beta has a high ionizing power. It's higher than gamma, but it's not as high as the highest ionizing power, which is alpha. Alpha radiation is the highest, has the highest ionizing power. And why does this matter? Why is this important? Well, this is particularly interesting for humans because radiation, such as these types of radiation from radioactivity, are generally considered unsafe. Other types of radiation are generally considered unsafe as well, such as like the radiation that comes from the sun, definitely would be considered to be dangerous. And the reason for this is because these types of radiation can knock electrons out of our molecules inside our body, particularly DNA. DNA is very susceptible to being ionized. So if you knock electrons out of DNA, you can essentially change its structure. And with that, that's what we call a mutation. And if you mutate your DNA, if you knock some of the electrons out, you change the structure, then you can potentially create damaged genes and lead to genetic diseases and cancers and stuff like that. So we are definitely wary or conscious of highly ionizing radiation is not something that we want to mess around with. It also does have applications though, and very important uses, which we're going to see in a future video. At this stage, we're ready to answer some questions about ionization. So I'm going to pause the video and do these questions for me. So from memory, I want you to complete these 3 sentences. Pause the video and do that now. Okay, so ionizing, what does it mean? Ionizing means knocking electrons out of an atom and creating an ion, or losing electrons from an atom and becoming an ion, so they become ions. But in this case, ionizing means we're using radiation to knock electrons out of another atom. The most ionizing radiation is, well, that would be alpha particles, and the least ionizing radiation is, that would be gamma radiation. So well done. If you got that right, we're ready to have a look at the next section. Okay, so we've seen that radiation leaves an unstable nuclei. It can be alpha, beta, or gamma radiation. Now they all move and travel at very high speeds. And the question is, how far can they travel? That's the next thing we're going to look at. How far is each type of radiation going to be able to travel? So if you I want you to imagine that we've got, stick with me now, it's a strange analogy, but it works. Imagine that we have an elephant. Okay, so we have an elephant and he's trying to run through a forest. Now, the elephant will easily bump into trees because it's so big. And when it bumps into trees, it's going to lose its energy and it's going to slow down and it's going to stop running. Okay, well, an alpha particle is kind of like that. An alpha particle is the biggest of all the particles. And as it leaves the nucleus, because it's so big, it's essentially going to crash into anything. So even something like air particles, it's going to crash into them. So as soon as it leaves the nucleus, it's encountering other particles. And because it's so big, it's crashing into them. So things like air or other materials that might be around the radioactive source. And when it does this, it's basically going to gain electrons as it crashes into other materials. And then it just becomes an ordinary helium atom. As we've seen already, an alpha particle is like a helium nucleus without the electrons. When it crashes into other atoms, it gains electrons and it becomes just a standard helium atom. Okay, now, how can we show this? Well, we talk about the range in air. Range in air. So an alpha particle, shown here by 2 protons and 2 neutrons, it has a very short range in air. It can only travel a few centimeters before it crashes into enough air particles to slow it down, take electrons from, and just turn into a standard helium atom. So it's got a very short range. It doesn't go very far from the nucleus. What about beta particles? Well, beta particles are what we call, they're just electrons. They're high energy electrons. But I want you to imagine that they're like a horse running through the same forest as the elephant. The horse will definitely not bump into trees as quickly as the elephant because it's smaller, but it will eventually hit the tree. And when it hits the tree, it's going to slow down, stop running, and essentially it's going to lose all that energy. It's probably, it's not as big and it's not as charged as its friend, the alpha particle, but it's definitely going to crash into something. So the beta particle is like an alpha particle. It's a bit smaller, but it's not going to crash into things just as easily, but eventually it is going to crash into stuff. So it's like the horse is a bit smaller than the elephant. It's able to get through more of the trees, but it's eventually going to hit something. So a beta particle can actually travel for about a meter in air, 1 meter in air. Eventually, it's going to hit some particle, and when it does, because it's an electron, it's essentially probably just going to attach itself to that atom. So if it's an atom or an ion that needs an electron, then the beta particle is going to become part of that atom. So it has a range of about 1 meter. The gamma radiation, if we think of the same analogy, gamma, is kind of like a bird in the forest. Okay. Now, what does that mean? Well, it means that they can fly and they can move in and out through the trees and they can dodge them. They very, very, very rarely ever crash into a tree. Okay, so the gamma radiation is kind of like that. It's able to move through materials without actually crashing into atoms because they're not actually physical particles. So if gamma radiation is just traveling through air, it's pretty much able to keep going for an unlimited distance. Okay, so there's basically only certain materials that can slow down the gamma ray. So we say it's nearly got an unlimited range just in air because it rarely crashes into any atoms. Okay, so that is its range in air. So gamma rays have the highest range. This leads us on to talking about something called penetrating power. Okay, so this is how far they can travel in air. What about penetrating power? Well, if we take our alpha particle again, we know it can travel a few centimeters in air. But it would be stopped if we put a sheet of paper in front of it. This would stop it. The alpha particle is too big, it crashes into the paper particles and it dies, it slows down. It gains electrons and becomes just a helium atom. The beta particle, usually if there's lots of beta particles being given out by a source, some of them will hit the paper and keep going. So they will pass through the paper. Alpha particles never will do this. Beta particles will hit the paper. Some of them will keep going through. But they would be stopped by a thin sheet of foil, metal foil, like aluminium, like tin foil that you use for cooking. So that thickness, aluminium foil, will stop beta particles. So alpha particles stopped by paper, beta particles stopped by aluminium foil. Gamma rays will easily pass through these two materials. Easily, okay? And in fact, it will take a block of lead that's a meter thick. So 1 meter of lead to stop gamma radiation. Or if we were using a material like concrete, it would take several meters of concrete. Okay, so because gamma rays are so small, the particles in the paper aren't packed together tightly enough to make the gamma rays hit it. Also in aluminium foil, the particles aren't packed together tight enough to make the gamma rays hit them. The lead is much more dense material than aluminium foil or paper. And if you have a meter thick of it, then it means that the gamma rays will, at some stage, will hit the atoms and slow down. With several meters of concrete, it is also possible to slow down, stop the gamma rays. With this, we talk about penetrating power. Alpha radiation has the lowest penetrating power. It's stopped by the sheet of paper, and it also only travels a few centimeters in air. Beta particles have what would we call it? Medium, mediocre, moderate maybe, moderate. It's higher than alpha particles. Moderate, yeah, sorry, moderate. It's higher than alpha particles, but it's lower than gamma radiation. Gamma radiation has a very high penetrating power. Okay, so this here is penetrating power. Okay, so gamma radiation has an unlimited range in air, and it can only be stopped by a meter of lead or several meters of concrete. Sorry, I forgot to write that it was concrete. Now again, you don't need to rush and take all this stuff down, guys. Just more important that you listen and understand. All right, so that is our range in air. So our properties we've looked at are how they act in an electric field, how much ionizing power they have, and their penetrating power or penetrating ability. It's time to do some practice. All right, so for these questions, what you have to do is say whether we're talking about alpha, beta, or gamma radiation. So first one, I'll do it for you. So made up of a single electron. Well, from alpha, beta, and gamma, I know that beta particles are made up of an electron. Okay, so you get the idea. I want you to pause the video and I want you to do the rest of these now, please. All right, so you should only be playing the video if you have done this all. Okay, so most ionizing type of radiation, most ionizing, that's alpha particles. They are the biggest and easiest to knock electrons out of atoms, alpha particles. Moves the shortest distance through air, that's also alpha particles. Bigger particles are easier to slow down. They hit more atoms. Takes 2 protons and 2 neutrons away from the nucleus. So when the nucleus spits out particles, which one would cause the nucleus to lose 2 protons and 2 neutrons? Oh, that's alpha again. Blocked by a few millimeters of aluminium, but not by paper. We should have said beta. Beta particles. Not made of any particles, that's gamma. Part of the electromagnetic spectrum. Well, an electromagnetic spectrum is a wave in which energy can be transferred. So this is gamma radiation because it's a wave, not a particle. Has 0 charge or has no charge, that is gamma. Has a +2 charge, that's alpha. Has 0 mass, gamma. Now you might have said beta there. Now beta has very, very small mass, but it's not zero. Okay, so it's very, very small, 1/1838 compared to a proton or a neutron, but it's still got some mass. Easily blocked by skin. I probably didn't really tell you that one. That's probably going to be alpha. Alpha would be equivalent to skin. Okay, so it's quite thin. Gamma radiation definitely gets through skin. Beta radiation might get through a little bit of your skin. Radiation with most mass, that's alpha. Well done if you got those right. Okay, one last thing for you to do, and that is to make a table which summarizes what we've learned here today. As you can see, I have done the first one for you. I have done the alpha particle. What do I want you to do? I want you to summarize what they are, what their charge is, what their mass is, how they are affected by an electric field, and their relative penetrating power. So that's what I want you to do. As you can see there, I have completed it there for the alpha particle. So you should do something similar for beta and gamma now. So you can pause the video, take down what I have in the outline of the table, and then complete it for beta and for gamma. Okay, that's it. I don't have the answer for you there now, so you need to make sure you go back through and make sure you have your facts right and have corrected. This will be a really useful summary table for when you're revising this particular chapter. Okay, that's it, guys. Thank you for joining, and I'll see you in the next video.